So today we will continue on to learning how to use pointers and first of all, why should we care? It's a confusing thing and seems from this point, it looks useless. So we'll tell you a lot of things pointer can do that is powerful, right? A quick recap. We have a discussion on data versus addresses. If I say int a equals 10, it means that I just declare a variable called a and it stores the data value of 10, right? Ampersand a means that I'm going to look at the address of where this value of 10 is. Technically, this means that I'm looking at this virtual address. We'll cover this in module 3. And this locate, give me the location, the exact location of where is that electron that I need to measure to get that value for address for the variable a. So to use a pointer, you can use a star to refer to a pointer, right? So here A is a pointer to store an address. If you type that line in C, I think it won't compile because you cannot initialize the value of the pointer at the same time as when you declare it. You have to malloc first. So some big quick caveat here. I need to type it in because I really want to save space for my slides. This address points to the location that has the data value of 10, right? And the star A, whenever you type star A, it will give you 10. You can use, if you have a variable, you can use ampersand to get an address, and you can use store on a pointer to get a value. You can make pointer points to other variables, and you can also do operation on pointer. This is like a recap of the end of last Thursday, right? And the next thing I want to tell you is this thing called a null pointer is again recap. Pointer points to something, a null pointer points to nothing. It's like when you initialize a pointer, you want to make sure it doesn't point to anything because it's not safe to use, right? So you can assign a value null, like literally type in NULL. It will make sure the program understand that, hey, that pointer doesn't point to anything yet, don't use it. Right? It will actually assign the value of 0 to that pointer. Data has its type and size. So in C, when you create a pointer, you want to be able to allocate the memory, right? To say, hey, I want a pointer that points to 10 integers. You can use the keyword size of plus the data type in or even size of some variable, it will give you the size of that thing if you put it as an input. It will check the data size. And you can allocate the memory. So if you use an array, this is done statically. When you run the program, the compiler and the runtime basically will say, hey, allocate that array for me whenever I start the program. Yay, right? It will be allocated in the stack. You can allocate things dynamically through a command called malloc. Whenever you call malloc, it's as if the computer go find a free location in DRAM, allocate that portion of your DRAM for the variable A. Think of it as if you go find an empty line that can fit 10 integer for A, and then A will take this address. Right? So this is kind of like a recap. Why should I care? It allows this thing called dynamic memory allocation, right? You can use it to implement linked list, some different type of data structure. We'll go through some of the details today. I will make assumption that you never took data structure class, so I can tell you, okay, how does the linked list look like? What's the tree and things like that. You can pass data into and out of the function. You can return more than one thing. You can use the function pointer, which we'll cover right now. So this is the new material from Thursday. We'll start to look into this thing called function pointer. And why can we use pointer to point to a function? If you think about it, the first time we start learning C, right, 2 weeks ago, I told you when I run a program, A program is stored in your memory. When you buy the memory, your DRAM, whenever you run something, the program is located there. Which means if you have a program stored somewhere in your DRAM, it means it has an address, right? It means that program has a home where you can point to using this thing called function pointer. How do you declare that? So this is our function. Oh, sorry. Let me use pen. Sorry. Here's our function, right? It's called func. The only thing it does is add 10 to A. It takes in an integer, add 10, spit out A plus 10, right? And here's the main function at the bottom. What does ampersand func give you? Func is a function name, right? So ampersand func, what do I get? The address of what? The address of that function. Perfect. Yeah. So the add is this address of that function first line. Basically, it gives you that address. It means that you can call the function, right? So let me use a different color here, right? Our function pointer is now called func pointer, right? Let's assume that's called func pointer. I can call it with a different name. I can call it cat, dog, hello, meow, or whatever, right? Just put some name there. To denote that this is a function pointer, you add in star in front here. Right? This is the same as when you create a pointer, right? You notice the int in front and int in parentheses, right? There are two new things here. There's int here and int here. 1 and 2. 1 is the input data type of that function. 2 is the return type. So that line literally means that I create this pointer that points to my function here. And I tell the compiler that this function will take an integer as an input because that number 1 I put in is say int, right? And it returns an integer. Let me give you one question. So let's say if my function takes in A and B, so let's say func2 takes in int A and int B, I guess I'm char C. And if I say I want to create a function pointer func2 and I call it func2 ptr, what do I put here? What do I put in this parenthesis at the end? I want it to make sure it takes in, and char. Yep, exactly, in and char. And let's say it return, I don't know, float. What do I put in front? I just put in float. Right. I need to put parenthesis over here to make sure this function pointer is treated like a function pointer. And that's it. Right? And you can call it using this line here, right? You first dereference the pointer saying, hey, I have this pointer. I want to use it as a function, put the star there. Similar to how you treat an address, right? You have an address, you want to convert that to a data, you put a star there. Over here, you have an address for a function, you want to convert this to a proper function, put a star there. Input for that function, 0. So this get called twice, yay, right? So it's the same thing as a typical function call, but you first dereference the function pointer. Any questions so far? All right. So if you have questions, feel free to keep typing. I'll look at the chat. But quick notes on function pointer. first of all, because when you run a program, that function is already allocated. It's somewhere in your memory, so you don't need to perform allocation. There's no malloc call needed. Just have a pointer point there. Fine. You can get the address of the function using the pointer. Basically, you can say, hey, new pointer ptr equal func pointer. That's fine. Just make sure when you do that, think about bad things you can do when you assign like different address that move around. Basically, you point to different lines of your code. So hopefully you don't overwrite that because it just literally means you just build a program that overwrite itself, right? And that can be dangerous. Pointer can be an array, so you now can have an array of function pointers. Override, yeah. This function of pointers works like a normal function. And many of the C like tools that are what we call libraries requires function pointers as an input. For example, there's a library called quicksort. It allows you to give in an array, and it will sort the array based on your function here. The function should give you if A is less than B. What do? If A is equal, basically you return -1 if A is less than B or equal to B or greater than B, depending on how you want to compare. If you want to do lowest to highest, then you return -1 if A is less than B. If you want to sort from highest to lowest, then you return 1 if A is less than B. Right? So you can use function pointer for that. You can use it as a callback function. So what's a callback function? It's basically it's a function that gets called when some event happens, right? Another example of function pointer is something like this. Let's say I have a function pointer that's called, I guess, function ptr, right? And I have two functions, function 1 and function 2, right? And if certain thing happen, I want to call function 1. But if another condition is met, I will call function 2 based on the condition. I can use function pointer for that. If this is true, func pointer now point to fun1. If this is false, func pointer now point to fun2. Then you call func pointer because you already set the correct function. Right? So this allows you to actually set functions that you want to call dynamically. That's it for function pointer. Now we'll move on to the next topic, which is how does data structure work in C. Exactly, yes, it's like a linked list. So we will now cover a little bit more complex structure. And I will make an assumption that not everyone here took data structure, not everyone here took algorithm, right? So I'm gonna start from ground up. Pointer is useful to implement things like linked list, tree. This is essential to computer science, actually. Just used everywhere. I cannot tell you. So one of the like really like intro question that if you want to work at some company, I can ask you to implement a linked list, right? So it should be kind of like in the backbone. I usually come up with a code, or at least a pseudo code of that, like in the back of your head, right? So pointers allow you to point to the next item. So a general guideline to create this data structure is, well, you create a struct that contains the data that you want to store and the pointer to the next items. Right? Optional, you can define its own type. And then you can declare a pointer that points to the first item, right? This can be a root in tree or the first item in the linked list. And then you use malloc to keep adding new things. And we'll play with this in our exercise and our assignment. But let me go through some basic concepts of data structure. By first talk about linked list. This is one of the most common data structure. Right? So what is a linked list? Can someone tell me what is a list? What is a list? Give me a human definition, like in English. If I say it's a list of things, what does it mean? It's a collection of something, right? That's the first thing that you need to notice. What's that? It has some order, right? That's the first item in the list, the next item in the list, and the last item in the list, right? Any questions so far? Basically, it's a collection and it has order. You can tell this is the fifth thing in the list, this is the seventh things in the list. So what can I use this for? This looks like an array, right? So let's say you have an array that looks like this. 1, 2, 4, 8, 7, 6, 3, 10, 11, 12. I ran out of number I want to put in. So let's say I want to insert a number 3 in this list or in this array actually. What do? I want to insert new items. Let's say I want to put in 14. I want to put in 14 here, but I ran out of space. What do? Yeah, create the new array, right? And basically you then do array prime. That's the bigger version of this array. Now you can say 1, 2, 4, 8, 7, 6, 3. Now I regret my decision to make a list so long. 11, 12, 14. And you have more space left, right? So you increase the size, right? So when you do this, what are the operations that happens? Malloc, right? You need a new array for sure. Copying the data. 1 get copy to 1, 2 copy to 2, 4 copy to 4, 8 copy to 8, blah, 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 right? So that's the overhead. In a linked list, this would look something like this. 1 point to 2, right? Point to 4. So if I want to insert 14 at the end, this is what it looks like. I just say, okay, I'm going to allocate one more block, 14, and make sure 12 point to this block, right? There's no copying, right? Do you see the difference now? So let me tell you one more thing. Let's say I want to insert. Let's say I want to insert. Give me some random number. Hopefully not too long because I don't want to write a lot of numbers. 9. Okay, perfect. So let's say I want to put 9 in here between 8 and 7, like right here. What can I do? Let's do 88 too. So let's say I want to do 88 right here. What do? Yeah, you reassign pointer, right? Make sure 8 points here and now 9 points here, get rid of this. 6 point to 88, 88 point to 3, get rid of this. Easy, right? Just reassign this pointer, right? So you see the flexibility, right, that this provides over an array. And the reason why I use the word flexibility rather than performance is keep thinking about this. When you go to module 3, we will cover this a little bit, but this assignment that can be like linked lists typically are slower than using an array. Using a linked list is typically slower than using an array, and there's certain reason why. But this is flexible. I can just dynamically increase the size of my list, right? So let's say I really, okay, this is nice. I want to build this in C. What do? I have a struct. Let's call it node, right? I'll just call everything a node. And I have a value that I want to store, right? So this is the value you want to store. What else do I need? Else do I need inside the node so that I can point to the next item? The next node, right? So I don't actually store the next node. I just need to store the pointer to the next node. So I can say struct node pointer next, right? This gives me a way to point to the next node, right? So visually, this is what it looks like. This is our node, right? This is value. This is next, which can point to the next thing. And if you want to say, hey, that's it. Oh, you mean this is a star? Yeah, it's a star. Sorry about my handwriting. Let me clearly write this. Okay. Value. Yeah, I love using this ground symbol for now. It points to nothing. So basically that's the end of my list, right? And then I can say struct node pointer front, which I can then assign so that it points to this element. What you get is a train. No, and you get a linked list, right? So you basically have front, the first item points to the second item. The second item points to the third item. Let's say you want to insert the new node here. What do? You then reassign, right? This to point to here, this node point to here, get rid of this. If you want to delete this node, what do? Yeah, cut the pointer. This now point to here, and then free this up, right? And in high level, that's it, right? I'll show you an example during the sample code section toward the end of the class. There's a pretty high chance I won't finish it, depending on how much time I have left, because I want to make sure I explain what I'm typing, while at the same time show the code, right? So it might take some time because I need to also explain what I'm typing as well. I'm gonna try my best to show the sample, and then we can follow up afterward. What is a queue? So that's the second set of data structure that we'll cover in this class. What is a queue in English? Well, I guess in the day-to-day life. Actually, that answer is harder than to define than to know what it is, right? Because yeah, it's the first in, first out. It's a collection where you come in first, you get to go out first. That's a queue. If you go to theme park and there's a line, you queue it up. If you are in front of the line, you will then get to write that the thing next, right? So that essentially definition of the queue. What can I use queue for? Actually, this is many things. A lot of things in computer, especially now, if you actually zoom into the computer system, computer hardware, there's a queue for many things. You want to access these data, queue up. There's also the other processor who want to access similar thing in DRAM. queue up. Literally, it actually makes those things queue up. You have 4 CPU, right? Let's say task manager, that's a great example, right? You have 4 CPU, is capable of running 4 to 8 things. If you buy Intel processor with hyper-threading support, you can run 8 things at once. If you don't have hyper-threading support, 4 CPU can run 4 things at the same time. How many Chrome tabs do you actually typically have when you browse something or just right now? Anyone have more than 10 tabs opening? Yeah, many of you did, right? And you all have 4 GB of memory. Oh my God. Yeah, and they would likely crash. So if you have a lot of Chrome tabs opening up, it needs to queue up to use the CPU. It actually takes turn using some kind of priority, right? It's not exactly the queue. Queue without like optimization for descheduling is not great. But you can use a queue for that. It's fair to some extent, but it's not fast. Uh, anyone here been to a theme park that has a fast lane and a normal lane? That's a long pause. Okay, so let's say you go to Disney World in Florida, right? There'll be a lane where if you pay this amount of money, well, actually they don't now. They make it fair. If you go to Universal and you want to queue up for the Harry Potter ride, right, in Florida, there'll be this fast pass lane where if you pay more money than the rest of the people, you get to queue up in this lane and you get to ride first. And then there's a normal lane where you will queue up like a normal human being, right? So you can use multiple queue in system to prioritize. Yeah, they have it in Singapore too, right? I think they also have it in Japan. But these are 2 queues, right? You have a priority queue where if you are in there, you get better service, you get more priority. So you can impose different priority. The same thing might happen in Linux too, right? Each task has different priority. If you send something to get printing out on a printer, who cares? If you print that thing out in the next minute, I don't care. If you print that paper out in the next 30 seconds, yeah, good, better, but I don't care. I care about it less than the task where you're playing games. Let's say you play, I don't know, one of like first person shooting game, right? Let's say I make a bad decision and bought Cyberpunk, right? And I'm about to get shot at by a bad guy. I probably care more about whether I can click and shoot at the bad guy than care more about how fast my printer is printing my job. Right? So different things in your computer has different priority. They can be on a different queue, right? Same concept. It's actually used everywhere. This thing is form one of the primary area in computer science called queuing theory, and they use a lot of queue. Actually, they use a lot of queue, and they have different priority that you can apply. The basis of it use a queue. Okay, so you can use queue for many things. In C, my recommendation, an array is a good way to implement a queue. So yes, let's say you have a queue in an array. How can you know if something is in the front? So let's say this is the content of my queue. 1, 2, 4, 8, 10, 12, right? I can have a pointer that points to, hey, that's a front. And the pointer that says that's a back of my queue, right? So what will happen if I want to insert something into my queue? I want to insert a new thing here. I want to insert number 9 in here. let's say this is called ARR. So I just say ARR back plus 1 equal 9, right? Basically, I put my 9 here. And then I say back plus, right? I move back right here. What if I want to DQ? DQ means I take something out of my queue. I want to take out this number. I just return ARR of front, right? And do front, or I guess front plus afterward, but you can't really do that in C. So one thing you can do is this. Return ARR of front plus. This will return 1 elsewhere, move front to here. Okay. Done, you got a queue. It's simple. Okay. You can even use the linked list for a queue. You can have a queue that have front right here. No, actually it's more like this. So it doesn't point to back. Oh, my bad. So this is queuing array. Is there a way to undo this? No. I accidentally hit erase all on this page. My bad. This is back. This is front. And this is your array, right? And this is if you want to use the linked list. Front, point to the next item, point to the next item, point to the next item, and that's it. And then you have back point here. You just then need to update front and back based on whether you want to end queue, which is putting new items in the queue at the back, or DQ, which is removing the front and move the front to the next item. Any questions so far? Okay, so a stack. What is a stack? A queue is first in, first out, right? You go in first, you get out first. A stack is called first in, last out, or last in, first out. Same thing. If you go in first, you are the last to be removed because they will remove the last thing that gets inserted. So this is what a stack would look like. You have a new item to put in here. You want to remove something, you remove the top, right? You remove the top things. What can I use it for? Tracing function calls. You have a lot of function calls. What do? You computer actually always handle the latest function call first, right? If you have Fibonacci of 5, Fibonacci of 4 plus 3, then you call Fibonacci of 3 plus 2 plus 2 plus 1, right? So a stack is implemented to handle this function call. Anyone heard of Stack Overflow? All right, so imagine a stack that look like this. And it's only go up to this much. Up to this much. What if I add 100 more things? You add function calls, what I can't add it. Yeah, so this is at that point you're like Stack Overflow. I have no way to trace your function call anymore. Too many function calls running out of memory. My bad. And crash, right? So that's what Stack Overflow means, because why do we use stack for? Tracing function calls, right? That's one way to use a stack. It's actually used in a lot of places in computer science. Similar to Q, we use these things everywhere. So it's good to know how to implement this. So the first version is the array version, which I'm gonna show you. Right? So let's say these are the value I have, right? Let's say I said this is the top, right? It grows to the right. If you add more things, it keep growing to the right. Right? So if I add 12, 12 will be here, now top will be here. If I add one more thing, what happened? Stack Overflow, right? I only have these many slots. Yeah, it go over the size, so Stack Overflow again. So this is the concept of the stack. There are two operations, push and pop. Push means I'm adding something. Pop means I'm removing something. So if I call pop at this point, you pop, right? This means you return 12, and now top will point to 11. Pop again, return 11. Top points to 10. You go one by one. If you push, then you put more things in on top of 10. Top will now move to that new item. Any questions so far? Okay, so we actually almost kind of like done before we go to the sample code, and before we go to binary tree, which is a kind of like a different beast. Let's take a quick break if that's okay. So let's do a quick break, 5 minutes. We'll meet again at 3. Is it okay? Yeah, we can go back. So questions? So a stack, when you have this, push, it means that you're moving this thing into the stack. Pop is you move thing out. You remove the top item out. Okay. In the meantime, I'm going to kind of like quickly get coffee as soon as possible because I kind of like uh sure. So that's a question about like you can use a linked list structure to build a hash map in the assignment. Yeah, you are definitely welcome to. I think for hash, but let me be honest here, right? For a hash map, uh use an array that contain a bunch of keys for the hash, and each array is a linked list might be better, if you know what I mean. For those of you who don't know what's the hashing, don't worry. We're not gonna cover it here. It's in our and the structure not touch it. I assume you took some of the one of those class before, so you asked that question. So yeah, you can use an array that correspond to each of the hash keys, as in like the result of hashing, for your linked list to remove, like to hopefully remove collision. Your goal here is to make sure linked list is as small as possible. Okay, so let's take a quick break. Like 5 minutes. I'll be right back. Need to refill my coffee, and we'll resume around 3 o'clock. Is that okay? All right, thank you. So we'll be right back at 3. All right, I'm back. Here. Okay, so are you all back? Oh, so let's continue with the binary tree. What is a tree? So for those of you who take data structure before, can you explain what is a tree? And we'll start from there. And that's a long pause. Okay, so I'll start with this. A tree has a root, right? That's in nature. Every tree has a root. If it doesn't have a root, it dies. So we have a root. And yes, so from the root, you can have a different amount of child, right? Tree. So it can branch out. It can branch out to say 4 child, 2 child, 1 child. If you look at the family tree in China, there's been 1 child in a while, right? Until I think they got rid of that a few years back. So this node can have again multiple childs, go through multiple levels, right? So this is a tree. It can be used to represent data, right? Any one of you here seen this picture of the COVID strand that branch out into now multiple strands? And that's like the dangerous ones, the one in England right now, and the one in South Africa right now, and the one in Brazil right now. There are 3 like really looking really bad strands out there. So you heard about that, right? You can actually trace these different strands of COVID-19 back to the root and see how it mutates, right? Using this concept of the tree, right? Basically, you start from the root, the one from Wuhan, branch out with based on different mutation in the DNA for the virus. Or is it RNA? It's an RNA. Actually, COVID is RNA virus. Basically, from the root, the one from Wuhan, right? You sequence the RNA, you get some patterns, you branch it out, you can see the mutation that happened, and now it's everywhere. Right? That's why you are doing online classes. That's why I don't get to teach in person, right? You can represent those data in a tree. The tree has a root. Each root contains a node that is a child. The child can have its own children. What does binary mean in English? Binary mean two, right? So it means that for a binary tree, or I would call it B tree, it means I can only have 2 childs, 2 children. My bad, my grammar. I can only have up to 2 children. This is a valid binary tree. 1 root, no child. No, it's okay. Doesn't violate my definition. This is also a valid binary tree. 1 root, and that root has 1 child. This is a valid binary tree. This is also a valid binary tree, but this is not. Because there's 3 childs here. 3 children here. My bad again on English. Sorry, I don't know what's happened to me right now. So this is a binary tree. Each node can only have up to 2 children. That's the binary tree. So what can I use binary tree for? It turns out this is one of the really, really common type of data structure that's used everywhere. You can use binary tree to sort things. This is called binary search tree. It allows you to maintain data and you can search quickly. You can use that. Yeah, actually network flow is another good example. I think that's tree, right? It doesn't have to be binary tree. I'm not sure, but I think you can just use a tree for that. A red-black tree is a form of binary tree with some constraint where you can implement each node representing by different color, and you can use that concept to basically index files in your hard drive for the file system. File system is a piece of software where you use it to manage the things like the actual location of the files. Let's say you double click on this folder, where does it go? Can I point to that file? Right. So that's tree. It's used actually in many places. And if you go and study data structure algorithm, this is one of the main data structure they'll cover. All the use in cryptocurrency as well. That part I'm not sure. Actually, I haven't really like tried to catch up to like this cryptocurrency much. I actually don't believe in that technology. Yeah, I'm not sure on that either. So if you're not sure on that, I'm not sure on that as well. So don't that take that as a grain of salt. I never heard about it use a binary tree. I think it just used some like consistency model to make sure everything eventually agrees on certain transactions. But let's come back to our class topic, right? So in C language, the binary tree can be constructed similarly, almost like a linked list, right? So what did we say earlier? If you have a linked list, you can start by using a struct node, right? And it doesn't have the name node. I just use this name for my convenience. I just want to name it node. Like you can name it cat. It's fine. Struct cat. You can name it whatever you want. Int value. And now that I have to point to two different things, right? So what do we do here? Linked list point to one thing, next, right? Now I have two pieces of next, the left side and the right side, right? So I can do this. Struct node star left and struct node star right. Right? This means that I just create this node that can point to the left side and the right side. Right? And this is how you can create a binary tree. In C, then you have a struct node root, which basically point to this location. You can then insert. Insert would put new node in here, right? So my question is this. So let's say I want to insert a new node over to this location. Now I'm going to violate the assumption of binary tree, right? I cannot have more than two children. What do? If you really want to insert this node here, right? What you would actually do is you can create a node here or a node here, it's somewhere in the at the bottom, right? As long as it's maintained the assumption that it's only have up to two children, depending on the algorithm, a binary search tree, for example, will insert a node at certain parts of your tree, depending on how you define the algorithm itself, right? Just as long as it doesn't break the assumption. You can then delete this a node. Let's say you want to delete this node. What do you do? So let's say you want to delete this node. I have this thing called left, right? How can I delete this node? What I can do is this. I can say make left point to here. Get rid of this link. Make sure this left now point to here, right? What would this look like? Something like this. Okay, so the right side is all the same. The side here is all the same as well. You just delete the node to the left. It now first point here and then point here again, right? That's the result of the deletion. The left bottom is gone. Now you have just this branch that came out, right? So what you are having here is, again, it depends on the algorithm because binary tree is used in multiple applications. Each application will have its own defined way of insertion and deletion for the node. Any questions here? So I believe in your assignment too, which I will release this Friday. You will see some implementation of binary tree will ask you to do this and will clearly define what you're supposed to do on insertion and deletion. Hopefully this will be a good practice because you then keep using the same thing again, again, and again, and again. Again, for C language, these are the reference for the class, and we do have in-class exercise for in-class exercise 4. But before we go through the in-class exercise, which I think might have to be done right after class or just like take-home exercise before the assignment, I'm gonna implement a linked list and do like a live coding session again. So let me switch over to Putty. In the meantime, if you have any questions, feel free to type in on the chat. So I'm gonna address them. So let me put a Putty here. Quick. All right, can you see my screen? Okay, sure. So there was a question about the submission for assignment 1, right? So that's a assignment 1 submission. So don't drop it on your home directory, drop it in this location. So if you go to root on sysq, you see this folder called hand in. You see this? So that's a submissions location for assignment 1 built already in A1. So if you look at current working directory, it's in /handin/A1. Submitted using, first of all, your user MUIC ID. So for example, there's already someone who's not letting me look at the code. Oh, I guess it's chmod 700. So make sure you do that too. Because when I'm actually grading this, I can change the permission so that I can read the files, but this would prevent you all from trolling with your friend's submission and make sure that your friends cannot modify your own submission. All right, so make sure you chmod 700 so that you have the submission there. So that's where you can submit the code. All right, any questions? Otherwise, let's go to lecture 7 sample code, right? I still have an empty file here, so I'm going to put in linked list C. And first thing, as usual, we have include stand.io in case I want to print things out, depending on how far I am. Main. Okay, so what's the first thing I have to do when I want to create a linked list? Oh yeah, that's a good answer. Yeah, create the node, right? Give me a name for my node. It can be any name. Train. Okay, sure. Struct train. In value, right? Something I want to store in the linked list. Struct train star point to the next item. And because I'm lazy, it is like a train, to be honest. So that's a great suggestion. Because I'm lazy, I don't want to type in struct train all the time. So I do type def, right? Train. Let me call it a node. Yeah. So I basically just renamed whatever you just type in. I'm just trolling you, my bad. So this I create a struct that consists of a value inside this, just not just the value, but the pointer to the next struct train, which is the next node in my linked list, right? So what else? I can do node star front, right? This basically means that I have this variable called front that can point to the front of my linked list. When I'm in main function, first thing I might want to make sure front equal now, so that hey, I haven't initialized anything. So let me make sure front is not pointing to anything. Let me do an insert. I want to insert a value into my linked list. What do I do? So tell me some edge cases. If I want to insert something, what are some of the possible edge cases that I can run into that can break your code? So I want to insert your number into something. When there's no more to go, actually that's a great edge cases. When you malloc and it return now, you ran out of memory, right? We'll cover that while we are implementing this. The other extreme end of the spectrum is when it's empty, right? When front is null. If front equals null. Okay, so if it's empty, what do we do? So let me say I create a pointer called temp that does the pointer to a node, right? So I can say temp equal malloc, right? Size of, what's it? What is the size of here? Size of, not exactly int, right? Because your node, this is a new node. So it should be size of node, right? Because it's an integer plus a pointer. So that's the size of node. So what we can do here is temp dot value, right? But the problem is temp is a pointer. So what you can do is put in here, star temp dot val equal value, right? There's a short form of that, which is basically temp val equal value. So let me put in comment. This is the same as I dereference temp first so that I got a struct, right? So this is the same thing. So let me delete this because it's kind of annoying to have this parenthesis star all the time. Temp val equal value. What's the next? What should temp next be? It's the first thing, right? So it should not point to any item next. So that's the first node. That's the first node you're creating. You want it to have the value. Next should be null because and then front equal temp, right? So let me format this a little bit. That's why I just think usually take longer. This is to make sure front points to A, right? Which A then point to now. You see this, right? Basically, any question here so far when you are, this is literally the first node. All right, so we're gonna cover the other end of the spectrum, which is we ran out of memory. We can't extend anymore, right? If we cannot extend anymore, malloc is going to return now. If malloc return now, oh, you can't do this. Basically, it will return now, right? So if temp, so if it return now, temp will have the value now, right? Return, let's say our error code is we just return -1. So over here we change it to integer, right? To make sure that hey, if I don't have any space anymore, just return. That's it. I can't allocate. I cannot insert, and I'll just return -1. Else, do this. All right, formatting done. Okay. And it doesn't like the fact that I forgot semicolon here. Okay, any questions so far for the just inserting the first node? And it still doesn't like my formatting. So anything wrong here that you can spot with the if else? Oh, okay. Oh, the -1 is just a return value, right? So you can return whatever you want. Over here, I just say, hey, I will assume that if I call insert and if it terminates correctly, I will assume that it's gonna maybe return 0. If I got -1, it means something is wrong with my insert. So I'm gonna have to look and try to see what's wrong with my code, right? This is for your program to interface with the user, saying, hey, something is wrong here. Can you come and look, right? It's kind of like the same thing as like when you run to blue screen, HTTP 404, right? You've been browsing Chrome before, right? What 404 mean? What does HTTP 404 mean? Yeah, it means the page is not found, right? That means that when you try to go to that location, it does return. It returns 404, which corresponds to the error code that is that means that hey, this address is not found. Over here, I can say -1 means I try to malloc and it doesn't give me the actual pointer. If it's if everything correct is correct, I'll just return 0. So this is what I can do. And I'm still not sure. Okay, I see why it has a red box here because I forgot one parenthesis right here. Yeah, sure. So the question is kind of explain shortly what malloc size of node means. Malloc, right, means I want to allocate, I want to book this area for this pointer. Malloc takes in a number. It's the number that represents how many bytes in terms of the size of something that you want to allocate. So over here, you want to allocate one single node, right? You want to add one thing to your list. That's why I say I want to malloc the size of the node. A node is now a data type because I define it right here, right? It's typed up. I define this data type. C will now know that, okay, whenever refer to node, it means this struct. What's in the struct? One integer, one pointer. How big is one integer? Right now it's 4 bytes. Or how big is one pointer? Assuming that it's a 64-bit machine, right? This is 8 bytes. So you get 12 bytes. Malloc will give you a chunk, like a 12-byte chunk of empty area assigned for temp, so you can use it later. So does it explain does it answer your question? Okay, awesome. So what else? What else do I have to do? All right, we'll go through this step by step. Yes, exactly. So the comment is like, is malloc kind of like new int square? So this is the question. Is malloc kind of like new int too? Yeah, exactly. It's kind of like calling new. New and malloc is kind of equivalent in spirit. Yeah. So if that helps, right? It's not exactly the same function call or the same sequence of things that would happen in the background, but in spirit, that's similar. New essentially instantiate the object, so it would initialize things for you. Malloc is more manual. It just gives you a block of space. What happens if you don't use it? At some point, you run out of memory, right? So malloc, it means I just book this land for you. If you don't use it, it's fine. But hopefully at some point you use it. Because if everyone wants to keep malloc and malloc and malloc and malloc, you run out of memory, right? If you see programs that use a lot of memory unnecessarily, sometimes it's because they just use a lot of malloc and are not trying to optimize for memory. So the amount of memory that the program uses is called memory footprint. It basically, as the name footprint suggests, right? When you run a program, let's say it's used 100 megabytes of DRAM, it means it has 100 megabytes of footprint. At some point, if all the program use a lot of this, it will compete for DRAM. It will make your computer a lot slower. So try to malloc things that you know you need and not more. And also when you don't need anything, free them. So you can say free temp later, right? When you know you don't need that block of memory. So hopefully that does clear things up a little bit. All right. So what should be the next case of things that I have to handle? So for insertion, can you, any one of you, can you tell me what should be the condition of where I insert things? Should I assume it's already sorted list and I need to find where to insert? Should I assume I will have another input that say location and I'll just insert at that location? Can give me something so I can make this, so that I can actually finish this function. Okay, to actually reduce the confusion, right? I'll just position. Basically means that if I call insert, right? Insert 5 and 2 will insert 5, the value 5 at the second index, which is making the list 1, 2, 5, 10, and 3. Okay, are we all agree on that assumption? Okay, so let's assume this assumption, right? So else if front not equal to null, which is basically else, now we want to find the position we want to insert, right? How do we do that? Well, one thing we can do is have another current, like another pointer to say this is the current position, and then I have a counter, right? So I want to count 2 positions, so I know exactly that's the position I want to go to. For counter equals 0, counter is less than position, right? Because I'm going to keep going. Counter plus plus. And because the for loop, I can only do one command, right? So every single iteration, I need to progress through my list, right? I need to progress through my list. So basically, this is what I'll do. Initially, I'll say current is front, right? I start pointing at the first item. When I move, now current equal to what? Current next, right? I just want to get another item. This is essentially exactly, this is running through the train, running from one node to another node to another node, right? So every time you iterate, you move one, I guess one bogie of the train, basically move from one node to the next node. What can prevent you from happening? What can prevent this from happening? The only thing that you need to make sure current next exists, right? I can throw you with this kind of input. So let's say if the input is like this, if list is 1, 2, 3, insert 5 at position 10 will insert, right? Insert 5 at the end, making the list 1, 2, 3, 5. Okay. So I can make that assumption, or I can basically return -2, another error code saying, hey, that position is not valid. Call again, right? So if that's the case, if current next is not there, we ran out in the list. The position is higher than the size of my list. What do I do? This is the last item we break, right? Don't go to the next item. This doesn't exist. Don't jump off the train. Go and stay at the last thing. Don't jump off the train, right? Otherwise, move on to the next item. Are you with me so far? Basically, now we're trying to find where to insert. Any questions so far? Let me clean this up a little bit because it's one line, so I can just combine this into the same line because I'm lazy. Can clean this up here as well. I can just say return -1 here to make the code looks more compact. In reality, it's not even like this is the same size. All right. If there's no more question, what do I do next? Now I know that I need to insert right after current. What do I do? Now current is the position you want to insert. We want to put the node right after this. Oh, first of all, malloc, right? You want to create a space for the new node you want to insert, type of node, right? If temp equals null, again, return -1, right? Else, insert. So if something is not wrong, what you do here? Temp val is equal what? Value, right? Temp next is, what's the next item? What should be the next item? Why now? Sorry for eating while teaching. I'm hungry. So, So this is kind of like where we are, right? How do we get C? C is essentially B next, right? Right? B next is pointing to C. What is B? B is current, so we do current next, right? If it's the last item, what is current next? Current next is null, so it's correct as well, right? What else do we have to do? So we are at B is still point to C, right? D now points to C as well. We only need to make B point to C, right? Are we on the same page here? We are at current. Current points to the next item, which is wrong. Temp also points to the next item. We want to make sure current points to temp, right? So we do this. Current next is temp. Are you with me? So actually, let me switch. So I think this is the good way to handle this. Let me switch to PowerPoint. You see my PowerPoint, right? So let's say this is our linked list. This is current. This is temp, right? What we do here, temp val equal value, is this is self-explanatory, right? That's fine. Temp next equal current next will be like this. Temp next is this thing, right? Current next is this, which point to this. So temp next equal current next means I'm doing this. With me so far? And then current next is temp is because current next still point to the wrong location. You want to get rid of this, right? Now it's point to this. Right? Any questions? And there's a one quick bug here. So this should be, oh, sorry. Undo. Where am I? Okay, here. There's a quick bug here because it should count to position -1. Why position -1? Let's say you want to insert 1, 2, 3, 4, right? And you want to insert here, right? So this is position 2, right? Position 2, so that you can, let's say you want to insert 5 at position 2. This means you want this 1, 2, 5, 3, 4, right? So yeah, so this is linked list, not a binary tree. Sorry for the confusion. So you want to insert 5 at position 2, which means you have to stop right at here when current point to 2. This is current, right? You want to stop right at when current points to 2. How many times current move? Only once, right? It go up once. From here, this is initially current is here. It moved from here to here. And that's it, right? So you want to make sure this is position -1, otherwise you go one step further than you want to be from where you want to be. All right. Another possibility, right? What if position is 0? We haven't covered that, right? We want to put it in the front of the list. So if position equals 0, do something here, else do this. So for those who use linked list a lot before, this will look kind of messy. I'm sorry, I just want to make sure it's like properly indented and clear so that you can analyze the code later. If position is 0, what do we do? Basically, we want to insert something at the front, right? Same thing here. Temp malloc, right? Oops. Then else, if we can allocate, right, do this. We want to insert at the front, right? So temp value, again, equal value. Temp next is what? You don't have current, but you know what's the front of the thing, right? Why is this the case? Let me switch back again to the slides, right? So this is a case where you have a linked list right here, and you want to insert something right here, right? Right here. So you see my screen, right? So what you have to do is, this is where front is. This is the new temp. So you just need to make sure this point to front, and then front from here points to temp, right? And that's it. Basically, that's the case here. And that's pretty much all. So I can say insert 1, 0, I guess at the position 0, insert 2, 0. Oops, bad. 5 and 10, it would insert at the end. 3 and 1, this will insert as a second item. And I hope I can compile. Oops, a bunch of error. So let's see what's going on here. So I need standard library for malloc. Okay, and then what else? Expected expression before no. So let's go to line 40. So first of all, let me add standard library because I need to call malloc. And then line 40. Size of node, my bad. This should be size of node. All right. This compiles, and hopefully there's no segmentation fault here. It does insert something. I haven't actually built a function to print the list out. So let me do that. Print list. NULL Pointer. While I can keep going, I will do this. Print F. Send D because I want to print some number. Make sure it looks kind of nice. So I have the comma here, and then node value. At the end, I will just say print F, node equal node next because I want to move on to the next item. To make sure I format this nicely, just do bracket at the beginning and bracket at the end to make it look kind of nice. So I put in front because I want to print the entire list. Okay, so I can do this and something is wrong. It's not value, it's called val. Right, so if I print it out, see 231. 231 because we first put in one, right? So this is basically make our list just one. You put two in front, so it's now two and one. This is five. Somehow five is gone, so there's a bug somewhere, right? It should be 215, and this should be 2315. So we missed this part where we are at the end here, right, at the end here. And I'm gonna fix that after class. So let me kind of fix this sometime. I'll ping you on an announcement because we are actually like running out of time. If you have to go join the next class, feel free to do it right now. In the meantime, I'll fix it essentially. So any questions? Actually, any last minute questions before we kind of finishing up and just fix this bug? Okay, so there seems to be an issue whenever I want to insert at the end. So I need to figure out why. It's likely is involving with something here. I might have missed like the link. So over here, if it's at the end, let me print out. So this is the condition where we are having some bugs right now. So I'll use GDB to do this, to actually fix this. Something is wrong here, right? And what line is this? It's line 63. So this is what I can do. I can GCC dash C dash O and G. Line 62. Line 63, 64. Stop at line 64. And do GDB. Link this and say break at line 64. And then, whoops. Break 64. Okay, so it loads. Break 64. All right, so I that's print something is wrong. Print 10. 10. Next. Print current. Okay, so it does print next correctly. So now current points to the end. And we say temp next is current next, or temp next is all right. Step current next should point to temp. So current should be at the same place. Print current next, which should now point to the at row. It should point to here. It does. The thing is wrong here. It should point to that number. If I print current next, it should show that number. Somehow it's not. Because I literally just say current next equal temp. Right? And current next is a pointer. Somehow it's still okay, so I'm gonna modify the code and I'm gonna create an announcement to to tell what's wrong. If that's okay. Since it just literally disconnect me. So let me reconnect again. So let me stop this.